Radia Perlman the first time, Jeff and Jeff?
When you were what?
When I first met Radia Perlman?
No.
The interesting thing is, so Mike Thibodeau and I were sitting at a bar, and I don't drink, so I mean we were drinking whatever else, and we were sitting at a bar in Washington D.C.
Yeah.
And up walks this lady and sits down right at the table and says, "I've heard you know something about EIGRP." And I said, "Well, could be." And she said, "I've heard that you claim that a distance vector protocol can converge faster than a link state protocol. And I do not believe it." And this, of course, was at 1:00 in the morning. So
sounds like
so did you feel argumentative? And how did you feel after?
What'd you say, Jeff T?
Sounds like ATF bar discussion.
It was an IATF bar discussion. 1:00 in the morning at the bar outside the hotel, or in the hotel at the IATF one year. I don't remember what year it was, many years ago.
Russ, you need to go to the left a bit. You're being cut.
Oh, is that better?
Your other left.
Yeah, something like that.
Hey, so I guess I should say hello to our audience here. Welcome to another episode. We're just swapping war stories here, or Radia Perlman stories anyway. Welcome to another episode of Between Two Nerds with me, Jeff Doyle, and my friend Jeff Tanzura. Hey, Jeff.
Hey, Jeff. Great to see you.
And
great to be here again.
Practically our third host these days. We've done several shows together. Russ White, thanks for joining us once again.
Yeah, sure. I think I'm in the right place now.
Yeah, absolutely. And we've been
and on the right mic now. I was on the wrong mic before. I was kind of echoey there.
Oh, you're talking about right place on the camera. I thought you meant you're in the right place as regarding this show. You know, you're definitely in the right place.
All of the above.
And as always, you can make a wish.
That's right.
But will it come true? I mean, I don't know.
No promises, but
yeah,
you never know.
You know, we're all IETF people. You know, dreams always come true, right?
Yeah, well,
it just takes time.
It just takes time. So anyway, we are continuing our discussion. If you've watched any of the last several shows that Russ has been with us on, Jeff and Russ have, let's see if I consider this, have, as I've already mentioned, one of my very favorite books, Navigating Network Complexity. Let's see if I can get that out. Well, anyway, you can see,
Jeff, if you pull it in and out of the camera really fast.
That's right. That's, you know, early special effects. And interestingly enough, the subtitle I've never really mentioned: Next Generation Routing with SDN, Service Virtualization, and Service Chaining. Maybe we should actually get to some of that at some point, but for now, I think we're just going to continue. We've been sort of just going along with what the chapters are, because the chapters are so well organized. And last time we talked about, we spent 3 shows already just defining complexity, and last show we wrapped up with measuring network complexity. And so maybe getting into, I don't want to say getting into practical topics, because it's been practical up to now too. But in this show is just the next chapter in line. I thought we'd talk about specifically operational complexity. And beyond that, there's design complexity, there's protocol complexity, and all of that. But operational complexity seems like a great place to start. I've jotted down a few notes from the book, excuse me, saying that you guys sort of lead off that chapter, you guys do lead off that chapter, talking about that there's 2 factors around operational complexity: human interaction with the system. Huge topic. Pretty much anytime you're talking about operations, the first thing that comes up is going to be the human factor, and policy dispersion versus optimal traffic handling, which is maybe a little more obscure, and certainly we want to get to that. But let's talk about human factors first. I've been jabbering on for a little bit. You guys feel free to jump in there somewhere.
No, don't want to interrupt you, Jeff.
Well, I'll just say this: the quote I've been using when I talk to audiences, probably for the last 25 years, under different contexts, is, that depending on what study you read, the human error accounts for somewhere between 65% and 80% of network outages. And I know that when I say that to audiences, there's always a lot of heads nodding when I say that. And yet I was saying that 25 years ago, and I still get head nods when I say that. Have we really done that much to get the human factor under control when operating complex networks?
Yes and no. I think that
if you're interested, I actually have a slide that shows exactly that. It's from Facebook operations, but
yeah,
1 time seen is better than 7 times heard. So
yeah, let's have a slide. Do I need some Jeopardy music to play while you're getting your slide up?
Probably not.
Hey, look at it. It's there.
Can you see it?
Yeah.
So this is sourced by Facebook. It's 3 years old, but I believe nothing really significantly changed. So if we look at the amount of outages caused by people touching stuff, really by changes, whether it's people or automation, and probably we should start with Facebook outage a few weeks ago, right? Yeah. It wasn't BGP, it wasn't DNS, it was a human mistake during change window, right? And then automation and scale took care of killing everything else. Practically, we are still, we being source of the changes are significantly contributing to number of outages. And you could see it's really, really more than failed hardware, than failed protocols, or something that breaks on itself. So think optics, cables, any hardware, right? So it's still us breaking the network.
So is it fair to say that using automation has made human error more efficient in breaking the network?
Yes, now we are breaking stuff at scale.
Yeah. And I think that's ultimately always going to be true, because what you have to do is attack the complexity of the network at the root, rather than just thinking that, oh, I can just automate and it'll be so much better. Fool with a tool is just a faster fool. That's just the way it works.
Yeah, certainly. And it's, I was making facetious comments, but, when anybody thinks about human error, the first thing most people think about is some guy sitting at a keyboard, typing into a CLI. And, I don't care how smart you are. Everybody makes mistakes when you're typing like that, and if you're me, you make 3 times as many as everybody else. And I guess the really important point there is that automation isn't a panacea for that. As we were saying and kind of joking about, if you may not be making typos into a CLI anymore, but you're still making human errors and just propagating them faster with automation.
You are, but you are making error. See, the thing is, we've moved the errors to a different place, essentially, is what we're doing. And we've moved them from making individual errors on individual devices is to moving them on to making a mistake in the automation system,
Mm-hmm.
which has much larger impact to, you know, the network overall. And I think that's why you get to the fool with the tool is just a faster fool kind of a thing, because you just can't, you're still going to make mistakes. And you can play games with, oh, you know, I'm going to have code reviews and I'm going to do CI testing. And I've been working around and in the coding world for ever since I got in networking and before. It doesn't, you're not going to solve you're not going to solve those problems with code reviews and CI and whatever else. You're just not. It's just an unfortunate side effect of being a person.
Can you?
And sorry, Jeff.
Go ahead,
so
Jeff.
we'll talk about kind of simulate, emulate, validate CI/CD pipeline next time we are talking. Actually, I have a few slides how we do it at Microsoft, at least high level. Practically, you always need to separate two things. It doesn't really matter how much it does matter, of course, but you test, you simulate, you validate before the change. There's always something that will go wrong at scale. Usually there's not enough coverage to, given the high variability of outcomes, to really validate everything, right? Think of BGP when you use your oldest path as the best one, which is behavior 90% of the vendors, RFC 5004, right?
Mm-hmm.
You don't know who is going to be your best path. You don't know who on the fabric is not going to receive your route, because best path, you'll see it's on ISN and potentially not to re-advertise it back, right? So there's not a lot, but there's some variability and unknown based on speed of propagation of updates, based on some artifacts of routing we cannot be aware pre-change, right? So on one side, we need to test. On another side, we need to contain. Even if something goes wrong, we need to reduce blast radius, right? And this is fundamental to working networking at scale. When you have cluster or pod or some other structure within which you can contain the error, and if it happens, okay, you take out the pod, but you still have another pod that can hopefully at application layer take over.
Right. And I, you know, I'll go back to the subject of the book, which is complexity, right? We need to focus on reducing the complexity as well, because the reason you don't know everything that's going to happen goes back to basically Keith's law, which is it's an abstracted system. Yeah. And guess what? I just can't know all of it. I just physically cannot know the entire system. So if you can't know the whole system, there's always going to be things where you push here and you think it's going to come out there and it actually comes out someplace different. You're just not going to get around that.
Mm-hmm. Well, how much of I mean, we've been kind of picking on Facebook here, but how much of the Facebook outage was due to still a human, you know, as you said, it was human error, you know, compounded by automation, but how much of it was human error that was not first validated before it was automated?
So kind of keeping it outside of speculation and kind of talks to friends what happened, the official statement was someone during the maintenance window typed a command that completely disconnected data center from their hub. So it's really someone doing the change and automation going wrong, because practically, I mean, proper is a good word. A properly coded system needs to do checkpointing, needs to catch obvious mistakes, and needs to have automatic rollback capabilities, right? And none of this happened.
Yeah. Yeah, hence my question around validation and how much validation can you build into your automation, and you know whether the automation itself, the validation itself is automated, or validation is procedural. You know, so saying, you know, don't run any of these changes in a live system until you first run it in a lab and that sort of thing. And
well, but even so, if you don't, if the whole system is so complex that you can't know the whole system, all of that is only going to catch some amount. It will catch more. You can catch more and more and more, but you will eventually find places where you're just not catching everything.
Yeah, absolutely. And I mean, I agree with you completely on that. And I guess I'm thinking in terms of, how do you reduce the obvious errors,
right?
So that then you can focus on the more complex and, the
right,
law of unintended consequences and the such.
Right.
And even if we take the simplest case, think basic underlay fabric will just be GP. There are 4 places where routes are halted, where it could go wrong, right? There is a BRIP or BGP RIP, so something wrong could go within BGP. There is basic RIP, so the place where you download your routes and you choose the best route to every destination. There is software FIP, or I don't know, CEF in Cisco terminology, and there is hardware FIP. All of them have their own synchronization mechanism, their own, if not best path selection, they try to choose the best route to a particular destination, right? So all these 4 have different semantics, have different metrics to choose the best route. And unless you can validate and compare all these 4, which is really, really complex, you're not comparing same data. Data is different with different semantics. So unless you can validate all these 4, you can never be 100% sure that you're actually going to forward traffic as intended.
Yeah.
If you put a VPN on top of that, you just added additional 17 layers.
And if you could validate all that, then you wouldn't need a routing protocol to start with. Because you would just know where everything should be and you could just configure it up and make it run.
Yeah.
And you would know every possible outcome for every possible problem. So in that case, why have a routing protocol? If you know what everything could happen is, then you know how to build every possible situation out, and you don't really need the routing protocol. It's just one of those things. So that's, I think where we don't always necessarily understand that this is inevitable. You're going to have problems. And what you really need to do is reduce the problem level, right? Like you're talking about, Jeff, right? As much as possible. And the second thing that you need to do is you need to just plan for failure.
Yeah.
Just expect it. It's going to happen.
And failures are inevitable. As we know, complex distributed system fail in funny ways. So being prepared that something is going to go wrong, right? For sure, one or another way, surely as important as being able to validate what you're doing right now. And probably monkey chaos is a very good example how you do this, right? You just kill stuff randomly and you see what happens.
Yeah. Talk a little bit about Chaos Monkey. I know that probably most people listening are familiar with Chaos Monkey, but in case you aren't, because it's a cool function application.
It came out of Netflix and had been open sourced. It's a system that randomly shuts down services and looks at outcome. So there's an expected outcome, but quite often the de facto the operational state doesn't match it. So you could go actually learn on your mistakes. If something happens, that's what's going to be the outcome, and then try to fine tune the system for the expected outcome to be actually what you see, or other way around, right? It allows you to build the know-how, how your system is failing, how it's going to fail, how it's going to be the end result. Either you could reduce number of surfaces, you could reduce number of interaction, actually change the way you interact with the system.
Yeah. And they actually do that on their production network, right? I mean, this is
not only network, it's also compute, right?
Yeah, it's compute
you
as well.
Service and you see
yeah,
how
absolutely. I guess maybe I should say the production IT. Maybe that's a better word. But the point is, they're not doing this isolated in a lab. They're doing it live.
Yeah, but I do think there are some misconceptions around this process. We tend to think of it, well, not misconceptions around the way they do it, but the way it can be done.
Mhm.
The way that my impression of the way Netflix does it and many other hyperscalers, not all of them, is they literally randomly pick different things and just fail them.
Yeah.
And they don't really, there's like blue team, red team type thing going on. And you don't necessarily, if you implement it in your network, need to do things that way, right? You can do more controlled experiments. Now, that said, the more controlled your experiment, the less likely you are to actually see what's going on in your network, right? There's a trade-off with all things. There's these trade-offs, and that's the trade-off in this particular case is the more you control what you're doing with something like Chaos Monkey, the less effective it's going to be at finding the things that are going to break in your network. It's just, the way things work.
Yeah, and probably it makes sense to separate simulation from emulation, right? Emulation allows you to do your testing fast and at scale. For example, it's easy to build machinery of BGP. Yeah. When you inject particular route, you know that everybody is going to run particular process, and the end of this process is going to be best path to particular destination, right? So you could actually emulate this behavior by simply building a bunch of containers running BGP best path selection. When you try to emulate, this is where it becomes more interesting, because now you've got control plane, you've got data plane, and unfortunately, emulation of data plane is not where it should be, right? In most cases, you might see difference between real ASIC or real hardware and software emulation as such. But this allows you to still test at scale, because deploying 1,000 VMs is easier than deploying 1,000 switches, right? So taking particular steps between building intent, what you're trying to do, and actually deploying it allows you to catch errors at different levels. And as we say, it's impossible to eliminate errors, at least reduce number of errors and severity of errors, hopefully, as you go down the step.
Right. And yeah, and I actually had someone say to me once when I was talking about Chaos Monkey, and they were like, I would never, ever bank at a company that did Chaos Monkey in their banking network. I'm like, well, why? Because it's so random and things could go wrong and you could lose your money and stuff like that. And I'm like, actually, I have exactly the opposite opinion. Show me a bank that does Chaos Monkey for real, I'm changing my accounts to them.
Yeah. Because, if you cannot plan errors and outages, if we could, life would have been great and easy. Practically, you need to be prepared for unknowns, and you don't know what you don't know. Again, things fail in very, very interesting ways.
How much you see? Trying to think how to frame the question best, but how much influence does the law of diminishing returns have? So that at some point, just the investment of trying to prevent errors becomes more expensive than just what the error itself would cause you. Do you see much of that?
I think it's a great question. And yeah, so it's all kind of very fresh experience and stuff I'm working on a daily basis. So there are two things. One is the price of actually getting the data. And as you go through the book, you will see very nice pictures and definition what is actually a programmable device and programmable network.
Yeah.
And it's very close to Russ's heart, being ex-co-chair of I2RS, which was trying to do this actually in ATF. And getting this data in coherent way from the device is really, really complicated. I mean, we are all seeing efforts in terms of GNMI, having GRIB to get stuff from and to RIP, having better interfaces, seeing streaming that actually delivers data very, very fast in structured way. But practically getting right data at right time from a device is still very complicated topic. And if you look at interfaces defined in the book in 2015, we still don't have them. Partially, yes, things are getting better, but we are very, very far. Another point is how much data you get, what you do with it. Imagine you've got system with, 100,000 routes. So if you need to analyze 100,000 routes, and again, as we said, even in most simple network, you've got at least 4 different databases that might have different views on your routing base. It's really complicated. However, if your network is layered, as an example, and potentially, if you could validate presence of default route in all 4 databases, which eventually might just result in 95% of your traffic going up the network, right? Yeah. It follows the default route. It goes someplace that has more or longer route, right? So in this case, even if you only validate default route present in BGP, in RIP, in software FIP, in hardware FIP, you've already eliminated 95% of possibilities for your traffic being black hole. So doing this kind of analysis and trade-off is very, very important because you might end up with huge database and what we call data that cannot be acted upon, which is worthless in network.
Right. And I think there's an interesting point there around the problem of why those interfaces we are looking for still don't exist. And I think that people kind of blame this on vendors, and I'm not sure that's really fair to me. Vendors, as hard as it is to believe, they have to make money. I know we don't like to talk about that, but that's the truth. They have to make money. And the way they make money is by differentiating themselves. And the more standardized the interfaces are, it's just a reality that it's harder for them to differentiate themselves. Not saying that they're trying to be evil, and go, oh, we're going to have an interface nobody else has because we don't want to interoperate. It's more like, I have this new innovative thing I want to do, but if I do this new innovative thing, it's not going to have the same interface that anybody else has.
Yeah.
Well, what do I do? Do I sit here and not do the new innovative thing because I'm going to get fussed at by customers about not having the same interface that everyone else has?
And all their competitors jumping in with the vendor lock-in song and dance.
Yeah, exactly. And so it's really, for a vendor, this is not an easy problem to solve. This is actually very, very hard. So I just, I wanted to jump in there and just say, don't beat up on the vendors all the time about this stuff. Sometimes it is lock-in, right? Let's be honest. Sometimes it is lock-in. Fine. Sometimes it's not.
Mm-hmm.
And you got to give people the benefit of a doubt about whether they're intentionally trying to lock you in versus just doing the best that they can given what they've been handed.
Yeah. And even so, your device might say vendor name on it. The ecosystem to build this device is really huge, right? Probably there are 50 to 100 sub-suppliers. And if you only looking at ASICs, we know all large vendors have their own ASIC, but also a lot of them sell something like Broadcom. So architecture of Broadcom is publicly available, well known, actually, but it's true for every ASIC. It has a particular number of interfaces. Some of them can be used for really passing traffic. Some of them can be used for memory because this is where you store your routes. This is how you access, how you look up your routes, right? And they're all finite resources. You could use them for one thing or another. Counters or anything that has to do with visibility is exactly that. You've got number of hardware resources allocated for counters. You try to use more, something else got to give. It's going to be either speed or number of routes or number of LSPs or number of MAC addresses. There's no free lunch. So when you ask for more visibility, usually this is at cost of something else. You're limited by size and amount of transistors on a resource, right? Mm-hmm. So to Russ's point, it's important to understand the trade-off between feature, scale, and visibility. You cannot have all three growing indefinitely. Something needs to give up to provide more hardware resource to something else.
Right. And I think a lot of people don't realize when you talk about telemetry and stuff that most of these devices that we're dealing with have essentially another entire internal network that is doing telemetry.
Mm-hmm.
Like this is not some, I don't know how to explain it, but it's not like there's, they're sitting there reusing the same gates or whatever. A lot of times they've built an entire internal network because you can't put telemetry on the same network with the customer traffic flowing through the device. Because if you do that, then you are hurting the performance of the device from the customer's perspective. There's no easy solution with a lot of these things. It's very complex. It's very hard.
And if you do it wrong, you can actually affect forwarding stuff. So you both work for Juniper now, and we all remember, I think 40s or so, they had very, very slow interface between PFE and RE, which is the hardware and the central CPU. So when you start using features like NetFlow that needs to go from ASIC towards central processor to be aggregated and normalized and everything else, I still remember it was early 2000. This interface we will go completely. So you wouldn't get not only NetFlow data, but you wouldn't get anything that had to go to the control plane. So it would pretty much kill the box. So again, as a router vendor, as a designer of a system, you need to understand the relationship between different planes or different layers in your device to provide enough capacity, enough resources to allow this data to move up and down in order to make it available to third party for analysis.
Right.
And, maybe that leads into, a different aspect of this, talking about operational complexity, and we're talking about telemetry and the such, and beyond the load it puts on the box, as we get better and better and more telemetry, maybe, is the load it puts on the operator themselves, and Jeff, I know we've sort of in the past done a lot of presentations talking about this, but operators are just flooded with this huge amount of information, and you can't really say, okay, I'm going to limit the amount of information I want, because different pieces of information, different data points become important at different times. And trying to sort out not only, is this important for what I need right now? And how does that relate to this other piece of data point, a piece of data over here? That becomes a huge challenge for an operator, and a huge need for analytical systems. Would you agree with that? To be able to sort through all that and say, here's what really matters to you at this moment.
And I think we spent indeed a lot of time with Jeff talking about relevancy of data and actionability of data, right?
Yeah.
Because there's really a lot of data. If you look at the amount of data that could be generated of large router today, when you enable all of streaming on all endpoints or every leaf that you could subscribe to, we are talking about terabits a day, right? In no way, if you in large network, can you correlate this data, or you would need to build something that's larger, more expensive than your production network, right? So you really need to strictly contain amount of data and quality of data. You get to high quality data, very, very little noise to kind of actionable data ratio, and very good understanding what are you doing and when you are doing it. And again, relating to Apstra, that common company for me and Jeff, we spent a lot of time trying to identify the telemetry that's directly relevant to service that is relevant to user's intent. So if your intent is to deploy, I don't know, BGP fabric, you're interested in this particular events and should simply ignore the rest because they're irrelevant.
Yeah. But this comes back to complexity again, doesn't it? This all comes back to complexity in one way or another, and how complex these systems are that they're generating this amount of data. And then we go back to what could you do as a designer or as somebody working on a network to not just say, okay, I want to, have less data, or I want to deal with, whatever it is. And one way you can do that is to reduce the number of protocols that you're running in the network. As stupid as that is, people don't think about it, right? We throw protocols at problems and we just don't think, could I really do this with something else that's already in the network? And there's a trade-off there. Again, it's not always the right thing to do, right? Sometimes it's the right thing to do to add that new protocol, but sometimes it's the right thing to do to say, yeah, I get it. You really want to run this protocol, but it's gonna do more than just add another set of configurations to your boxes. It's going to add another
It's additional surface that is going to interact with everything else. And I think we bring LDP IGP sync in every meeting, right? It's one of the most hated features, buggy as hell, cause so many outages and problems. Why? Because you have two protocols that have very different semantics, do different things, but need to synchronize with each other. This is the worst possible scenario.
Yeah. And so that's, goes back to the whole thing of how do I reduce the complexity? How do I think about complexity and think about what I'm doing to my system and its overall complexity as a system, and try to just reduce that to some degree.
Something, we were talking about Juniper, and my first stint at Juniper way back when Juniper was a startup. And we were doing a lot of work, as Jeff, you just mentioned, around MPLS traffic engineering, and being, typical nerd. I love that stuff just because it was cool what you could do with it and the such. And an early Juniper customer, I don't know why I can't name them. It was level 3 communications. I was sitting in a meeting with them and really touting all of this, the amazing things you could do with MPLS TE. And their chief architect, this was late 1990s, maybe, chief architect threw cold water all over what I was doing in the middle of it. Said, if I could build my entire core network with a bunch of big, dumb Ethernet boxes, I would do that. And that has been a lesson I've taken with me ever since then, around unnecessary complexity and as I mentioned earlier, law of diminishing returns.
Yeah, I think that's very valid. And if you think about it, in the data center space, we built up this very, very complex hierarchical design system, which works really well in the WAN in many cases. But you kind of wonder when you start looking at a data center, and I talk all the time about, what really happened is we had these issues with, with east-west traffic growing because applications were changing. Frankly, a lot of what happened that we don't like to talk about is that these networks just got too stinking complex. And people just stopped caring, and they just wanted to stop working on them. And so what we did is we came along and we said, hey, you know what? We'll do this other thing, this spine and leaf. Yeah. And yet what we've kind of done in many ways is we've kind of said, yeah, we have this cool new spine and leaf idea, and we're going to add complexity to it because, hey, all the complexity's been gone. Now that it's gone, let's go add it back.
Yeah. Yeah. And
just maybe different levels, right? We had to change the way BGP worked really significantly. All the knobs you see on data center network to allow to run best path selection across different ISs, and that would result in the ECMP set. Really ugly stuff like allow your own ISN. We all know the stuff, right? It adds a huge amount of complexity. It actually, if not breaks, it affects BGP in pretty bad way. BGP has very, very easy to understand state machines. As you start doing this stuff, suddenly you don't know anymore. When you start reflecting your route 25 times across your network, you don't know what's going to happen. So that brings predictability, and practically we introduce this complexity in order to make things work, because without it wouldn't. We would end up with single paths if we cannot compare paths coming from two different peers, right? But again, you need to choose where you add complexity. You build really different and much more difficult to understand physical architecture. I don't know, something like Balancer, or what we use in machine learning, which is not Liechtenstein. Or you build very simple fabric hardware, but then you bring this complexity in control plane that has to deal with it in order to, if not abstract, at least to hide it.
Which, leads to one of my favorite sayings, and I think I've probably said it in the context of these last few shows, and maybe I even first heard it from one of you guys, is you can't really reduce complexity. All you can do is move it around.
Yeah, you can toss it over.
I think Rift is a very good example. We spent, 3-4 meetings with Rift. You see that the underlying fabric is really, really simple. It's really like Tony likes to call it. It's like putting memory chip in the computer. It will just start working. But if you look into insides of protocols and everything else that's gone into Rift, it's really, really complex. So the complexity didn't disappear. It just moved and became guts of protocol. And since most people who operate the protocol, I mean, maybe not most, but a lot of people don't really care what's inside. From their perspective, thing has become completely simple. Just a black box, you plug another thing into it and just working like memory on a server, right? But complexity is still there. And when it breaks inside, God help you.
Yeah, I mean, some of what, when I think this can apply to most any solution. When I talk about Apstra to customers, a lot of times I'll talk about how Apstra is taking a lot of complexity under the hood and making that easy for your operators to operate your network and all that sort of thing. But the part that also needs to be considered, and this is, this applies to protocols and all sorts of things, is, there's still times when you have to troubleshoot it. And that's when you have to get under the hood with the complexity and figure out, the effects there.
Yeah.
And sorry, Russ.
No, that's fine. I was just gonna say, yeah. I mean, in this case, quite often you're trading off mean time to deploy something against mean time to repair something.
Yeah.
And it's so easy to hide the mean time to repair under this huge, I don't really care because, it's something down the road, blah, blah, blah. This is our version of tech debt.
Exactly. And, and that's where, so many people, when you hear about, this product, simplifies your network operations, that doesn't mean, now you can get rid of all of your experts. They're still needed. But, it just, they're needed really more where they're really needed instead of,
but then that kind of raises a question, right? How do you keep your experts as experts if they're no longer practicing? And I actually don't know the answer to that question, by the way. That is something that I don't actually know how to answer.
That's a good question. And I think we could actually build a whole show around that. I'm looking at the time here, and our producer just reminded me that we're coming up on closing time. So that's actually a good place to stop there, Russ, because I think you maybe just suggested an idea for another show somewhere out there in the future. But in the meantime, I'm gonna let's go ahead and wrap things up for today. And Jeff, Russ, as usual, it's always been great having a conversation with you. And for those of you in the audience, again, as always, be sure to like us on Facebook and follow us, subscribe to us on YouTube, and we'll see you next time. Bye, guys.
Bye, everyone.